task was to analyze COVID-19 data and train a model to classify either mortality risk or severity based on patient data. The dataset we used is called Mortality Risk Clinical Data of COVID-19 Patients. It's a cleaned dataset containing extensive clinical measurements and demographic details. The dataset provides essential information about COVID-19 patients admitted to a healthcare system during 2 distinct periods, the first and second 3 weeks of the pandemic. It includes data such as demographics, age, race, ethnicity, comorbidities, lab results. This information is crucial in predicting mortality risk or severe cases early in hospital admission. Such predictions can help optimize hospital resources like ICU beds and oxygen cylinders, potentially saving lives. Here are the key columns in our dataset. LOSF indicates how long the patient stayed in the hospital, death, age and severity, race, and ethnicity columns, comorbidity indicators, clinical measurements. The first step in data processing was to transform the non-numeric column age into a numerical representation. Using one-hot encoding, we created 4 new columns, each representing a specific age category, with values of 0 or 1. After this transformation, we normalized the dataset to scale the numeric values appropriately. Normalization ensures that all features contribute equally to the model training process, avoiding bias towards features with larger scales. Our next step was to split the dataset into train, test, and validation sets. To ensure balanced distributions, we combined the columns race, age, and death into a single column, and performed the split based on this combined feature. This approach allowed us to maintain an equal distribution of race, age, and mortality outcomes across all sets. Here, you can see the resulting distribution visualized in this graph. In this step, we prepared the data for training, validation, and testing. First, we separated the features and target variable. The death column, which indicates the mortality outcome, was extracted as the target variable. To address potential class imbalance in the dataset, we calculated class weights. Class weights help the model assign appropriate importance to both positive and negative cases of the target variable, ensuring balanced learning. These weights were computed using the class_weight module and passed to the model during training. We built a feed-forward neural network using Keras with the following structure. Input layer accepts all feature columns. Region layers. 3 dense layers with 128, 64, and 32 neurons, each using ReLU activation for non-linear transformations. Dropout added after each hidden layer to reduce overfitting by randomly deactivating 50% of the neurons during training. Output layer. A single neuron with a sigmoid activation function to predict binary mortality outcomes, 0 or 1. The model was compiled with the ADAM optimizer, learning rate 0.1, binary cross-entropy as the loss function, and accuracy as the evaluation metric. The model was trained for 60 epochs. Finally, we plotted the training and validation loss and accuracy over the epochs to monitor the model's performance. The loss graph shows how well the model is minimizing the error. The accuracy graph shows how well the model is predicting correctly during training and validation. Our next exploration focused on finding the best combination of parameters for the model. The first step in this process was testing principal component analysis, PCA, to reduce the dimensionality of our dataset. PCA identifies the most significant features by transforming the data into a set of orthogonal components that capture the maximum variance. Through experimentation, we found that selecting 18 features using PCA provided the best accuracy for our model. This dimensionality reduction not only improved model performance, but also reduced computational complexity, allowing the model to focus on the most informative aspects of the data. In our pursuit of optimal feature selection, we explored the use of a genetic algorithm, GA. This evolutionary approach allowed us to identify the most relevant features for predicting the target variable, death. We began by initializing a random population of binary chromosomes, where each bit represents whether a particular feature is selected, 1 or not, 0. Each chromosome's fitness was evaluated using a neural network classifier wrapped with Scorch for compatibility with client. Accuracy was computed through cross-validation, and a penalty term was added to prefer a smaller number of features. Genetic operators. Selection. We implemented tournament selection to choose parents based on their fitness. Over. A single-point crossover operator was applied to create offspring, ensuring a mix of parent traits. Mutation. Each bit in the chromosome had a small probability of flipping, promoting genetic diversity. Over 300 generations, the population evolved as the algorithm optimized the feature set. After each generation, fitness values were updated. The best-performing chromosomes were retained for the next generation. After running the genetic algorithm for feature selection, the optimal feature set contained 39 features. We compared these features with those selected by PCA to identify overlaps and differences. Both methods identified the following several features as highly significant: length of stay, AIDS, temperature, mean arterial pressure, blood urea nitrogen, sodium, glucose, lymphocytes, interleukin-6, procalcitonin, troponin. These features are likely fundamental indicators of patient health and mortality risk, as both methods selected them despite using different underlying mechanisms. Features only in PCA. Other brain lesions. International normalized ratio. PCA tends to emphasize global variance in the data, and these features may have been selected because they capture broader patterns or are correlated with other major variables. Features unique to the genetic algorithm. A star. Severity. Base info. Chronic obstructive pulmonary disease. Diabetes mellitus. Stroke. History of other neurological disorders. Oxygen saturation. Aspartate transaminase. Alanine transaminase. Ferritin. B-reactive protein. The overlap of features between GA and PCA reflects their shared ability to pinpoint key contributors to patient outcomes. However, the genetic algorithm's focus on domain-relevant, interpretable features provides an edge in practical medical applications. GA Advantage captures domain-specific insights that may not align with pure statistical variance, as in PCA. For example, race info and severity are likely critical for stratified risk prediction. In addition to PCA and genetic algorithm, we explored several other techniques for selecting the best set of features. These methods included independent component analysis, ACA, non-negative matrix factorization, NMF, and T-distributed stochastic neighbor embedding, SCN. However, the accuracy achieved with these methods was lower compared to PCA and the genetic algorithm. Here's a summary of the accuracy and the number of features selected by each method. PCA, 82.93%, PCA, achieved the highest accuracy, suggesting that dimensionality reduction focused on variance captured the most critical aspects of the data for predicting the outcome. Genetic algorithm, 81.57%. The GA method performed slightly below PCA, but provided a more domain-specific set of features which could be useful for understanding the factors driving the predictions. EA 75.80%, independent component analysis, while effective for separating independent sources of variance, did not provide as strong a performance in this task. The accuracy was noticeably lower than PCA and GA. NMF 75.63%. Non-negative matrix factorization, which decomposes the data into parts with non-negative values, also did not perform as well as PCA or GA. This method might be useful for applications involving parts-based representations, but in this case, it did not improve accuracy. TSA. Although TSNE is commonly used for visualizing high-dimensional data, it's not ideal for feature selection in predictive modeling. Its accuracy was also lower than PCA and GA, suggesting that it does not generalize well to this task. In conclusion, in our exploration of various feature selection methods, we found that PCA emerged as the most effective technique, achieving the highest accuracy of 82.93%. This suggests that reducing the feature space by focusing on the variance in the data provided the most meaningful subset for predicting the target variable. The genetic algorithm with an accuracy of 81.57%. Closely followed PCA and offered additional insights into the importance of specific features, which could be valuable for understanding underlying patterns in the data, especially in medical contexts.